Hello everyone. Today I'm going to talk about information flow analysis targeting Android apps. First, I'd like to talk about taint trackers that detect suspicious apps on the Android platform. Android apps have rapidly increased on Android app stores. In order to detect malicious apps, analysis techniques have been developed in the past decade. Bytecode level taint tracking is a common approach employed by many current tools such as VTDroid. The tracker interprets apps bytecode instructions on the runtime layer. First, the tracker marks a register as tainted at some input point or taint source. Then, the tracker propagates the taint from the register to other registers based on taint propagation rules defined for each bytecode instruction. As a result, registers holding values derived from the taint source are marked as tainted. The tracker checks taint at an output point or taint sink and identifies the information flow from the input to output points. To detect suspicious apps, the tracker should not miss information flows. However, an app can circumvent the tracker by calling API methods that transfer information through the system layers, including native and core libraries and the Linux kernel. It is called the Anti-Taint-Analysis technique. The invoke op instruction calls the API method with x as an argument. Then the other invoke op obtains the value into y. As a result, y holds the same value as x, but the taint of x is not propagated to y. Our goal is to detect such flow and propagate the taint from x to y. Next, let me explain the anti-taint analysis techniques. I'd like to focus on how the system layers enable an app to evade current trackers. Information flows are classified into 4 types: direct assignment, memory operation, control dependence, and the timing channel. First, direct assignment. Direct assignment flows are based on data flows. Data is transferred through media in the system layers. The context tainting tracker, or CTT, utilizes a predefined list of API methods that access the system layers to track such flows. However, it is impractical to list all exploitable API methods, and the tracker will miss flows when unlisted methods are used. The tracker can also increase false positives because it does not consider whether information flows occur. Secondly, memory operation. Memory operation flows are based on objects. Information can be stored in a specified location or used to specify a location to store another value. The object tracker propagates taint among reference type arguments, base objects, and return values of API methods. It can track some memory operation flows. However, the tracker fails for methods taking primitive data type arguments. Thirdly, control dependence. Control dependence flows, also called implicit flows, occur from a branch executed with x as an operand to a control-dependent instruction executed between the branch and its reconvergence point. The implicit flow tracker checks whether the information is preserved between x to another register at the reconvergence point. However, control-dependent instructions can store untainted values into the system layers, and the values are loaded into y by instructions executed after the reconvergence point. As a result, the tracker cannot perform the checking and fails to propagate the taint. Lastly, timing channel. In timing channels, data is encoded into timing by delaying program execution depending on x's value. CTT detects the execution of strip API method to track timing channel flows. On the other hand, the system layers supply more options for apps to cause timing channels. For example, the strip command. Only tracking timing channel flows on the runtime layer will fail to detect timing channel flows in the system layers. Now I will describe our approach, value-based tracking of information flows. Value logging and matching detects the flows and propagate taint based on data values, additionally to the traditional bytecode level tracking. Our approach intercepts operand values of the invoke op instruction, which may access the system layers. Before each execution of the instruction, our approach logs values of its tainted operands. After each execution of the instruction, our approach logs values of its untainted operands. The value matching compares captured values. When a new value is logged without taint, our approach checks whether the value equals values logged with taint. If two values are identical, the taint is propagated between them. In contrast, the matching fails when the system layers execute commands which can obfuscate data, such as base64. In this case, y holds the encoded value. Our approach detects commands and logs this value by executing the first command. As a result, the values are matched and the taint is correctly propagated. The value logging and matching, or VLM, track the four types of information flow occurring through the system layers. First, direct assignment. VLM detects direct assignment flows between X and Y. VLM requires no list of methods so that it can detect information flows occurring through unknown media in the system layers. Secondary, memory operation. For memory operation flows, VLM are ineffective because transferred values can be changed. Hence, our approach tracks objects considering primitive data type arguments. Thirdly, control dependence. VLM detects the Y flow, which is from a control-dependent instruction to Y. Then, our approach performs implicit flow tracking between X and Y. It checks whether the information is preserved between the registers. Finally, timing channel. To track timing channel flows in the system layers, detecting information flows between the at and the shell commands is essential, which is achieved by VLM. VLM detects information flows from an up to system commands, which are flagged as timing channel if the 3 or 4 command is executed. Up to this point, I have explained how VLM tracks the 4 types of information flows. For more details, please refer to our paper. Next, let me describe the evaluation. We implemented our approach into our taint tracking tool called VTDroid. We evaluated VTDroid compared with two current trackers, TaintDroid and CTT. First, we want to know whether VTDroid is more effective for tracking the information flows. We created a test suite based on ScrapDroid, a proof of concept of 16 anti-taint-analysis techniques. Our test suite contains 34 techniques relating to the 4 types of information flow. Next, we investigated whether VTDroid is more accurate in the analysis of real-world apps. The 3 tools analyzed 30 popular apps from Google Play in the context of privacy leak detection. I explained the metrics used. True positive means an actual leak-causing app detected by a tool. False positive means a no leak-causing app falsely detected by a tool. And false negative means an actual leak-causing app not detected by a tool, but detected by the others. The table shows the results with the 34 anti-taint analysis techniques in our test suite. VTDroid successfully detects all the techniques. By contrast, CTT detects 8 techniques, and TaintDroid fails to detect any technique. Hence, VTDroid is more effective for tracking the information flows. Next, I will present experimental results with the popular Google Play apps. The graphs from left to right show the numbers of true positive, false negative, and false positive, respectively. The colors indicate leaked information such as IMEI and phone number. The graphs in the left and center indicate that VTDroid and CTT detect 5 leaks that TaintDroid fails to detect. VTDroid detects the leaks with memory operation tracking. In addition, as the graph on the right shows, there are noticeable differences between false positive numbers of VTDroid and CTT. VTDroid triggers 3 more false positives than TaintDroid, while CTT triggers 33 more false positives. Therefore, CTT is inefficient in practice, and VTDroid is more accurate in analyzing real-world apps. In closing, I'd like to emphasize the following points once again. The system layers enable an app to evade current bytecode level trackers. Our value logging and matching detect the 4 types of information flow even when unknown media are utilized in the system layers. We built a taint tracker called the VTDroid, which is released with our test suite. We evaluated VTDroid compared with 2 current trackers, TaintDroid and CTT. The results show that VTDroid outperforms the current trackers. Thank you for listening. If you have any questions, please feel free to ask.